All right, so the next part, or the next process that we're gonna do on this part here is we're gonna create this pocket. This is a pocket from the top view here. We are looking down and it is gonna be recessed down inside of the part. So basically kind of around, or it surrounds our holes that we just put into it. And it goes in 250 thousandths deep. So there's the hidden line, that's the cavity of what we're trying to create. So it's a recess inside of there. The one thing that's critical on this that we pay attention to is this radius of 190. That radius is going to dictate exactly what size tool we should use to create this pocket. Now, so far we've given you 3 tools. You've got a 1/2 inch end mill, a 3/8 end mill, and a 1/4 inch end mill. So the way radiuses work in machining and just in general, this is just general geometry. If we go here and look at any tool, basically you have your center point and your circumference that goes around there, and the line that goes all the way through the center is the diameter. Okay, so the diameter crosses from one side of the circumference through the center line all the way to the other side of the circumference. And then we have another line which is the radius. So the radius goes from one point on the circumference just directly to the center point. So when we look at these in relationship, the radius is always exactly half of what the diameter is. So this goes for tools as well. So if we have a tool that's, say, 1 inch in diameter, let's say this measures 1.0, well, that means the radius is going to be 500 thousandths, just exactly half every single time. So if you're gonna machine, like what we're going to be doing is machining a corner in a part, basically what's happening is we have one edge here, and then we're gonna have one edge there, and we have a radius call out here. So on our drawing, we can see the radius is called out at 190 thousandths. So it's the same concept of what's going on here with the geometry. We just need to figure out, okay, well, if it's a radius of 190, then I need a tool that is twice that size. So if I go to my calculator and I go 0.190 times 2, I'm going to look for 380 thousandths. Well, let's go to our Starrett chart. And if I look at this here, I'm looking at options 358, then it goes up here. So the closest thing I have is a V, which is 377, but unfortunately they don't make end mills in that size. But what we do have right above it is a 3/8. So that's 375 thousandths of an inch. So that's a nominal size. Again, that's one of the sizes you have. So we look at that, but that's not quite right. So let's go back and look at it. So we're thinking it's 3/8, but is that gonna work for what we're trying to do? Well, if I look at my blueprint and go back to this, if instead of it being 1 inch here, this measures 375, we go and say, okay, 0.375 divided by 2, because the radius is half of that. All right, that comes out at 187.5. So that's the radius that a 375 tool is gonna generate. If we go back to our blueprint, it's called out at 190 thousandths, so 0.190. But since it's called out that way and it's only called out 2 decimal places, we go down to our drawing, in 2 decimal places we get plus or minus 5 thousandths. Well, if we're looking for 190 and we're going to achieve 187.5, we are within specification. We will still meet that tolerance and it will still be considered good. So we just know that even though it says 190, we're only going to achieve 187. And this is reality in machining. Sometimes you're gonna get as close as you can, hit the tolerance, and use the tools that you have. So with all that gibberish I just yacked about, we are going to determine that we are going to use a 3/8 end mill to create this whole pocket. And then notice when it says this here, radius of 190 tip, that means typical. That means that each one of those corners needs to be 190 thousandths. So, all right, so there's our geometry lesson for the day. Now we're gonna go back to actually how to produce this. So I went through and threw some Dykem on my part. There's a few different ways you could create this pocket. You can do it by edge finding and setting exact numbers, but it gets to be really skewed because you're going to have, give me an example. All right, so here's a 3/8 end mill. if I go and I edge find to this corner like we've been doing previously, what's going to happen is my end mill is going to be sitting, let's go this way, directly on the edge of that corner. So to get to, you know, this corner inside of here, what it needs to be, I can't just use the drawing dimensions. I would have to compensate for the radius of the tool horizontally and vertically to get it into the right location. So that means I'm adding some numbers onto the actual location that the blueprint shows, which is 380 thousandths. Well, then it gets weird because now when I come down to this side, I'm actually going to be subtracting the radius off. And I'm probably confusing you already, so that's why I'm not going to demonstrate it being done that way. We're going to go a little bit old school here, and we're going to go back to the scribing technique. So the way this is drawn, each one of these wall thicknesses is 380 thousandths. So it's 380 thousandths there, it's 380 thousandths here, it's 380 thousandths in this direction, and 380 thousandths there. So all of the edges are 380 thousandths wide. So what I'm going to do is put our angle plate up here, and I am going to take our part and the height gauge. We're going to zero right on top of here. We're going to move it down exactly 380 thousandths. And from there, we're going to go and just scratch it. And I'm just going to do the old rotation trick here and scratch it 4 times. And now that we're done, we can see a nice square on our part. Now remember, we still have our origin corner marked here with the red. Our origin corner is up in that upper left. So that's how I'm gonna orient it when I do machine it, just so I can kind of keep an eye on things there. Realistically, it really wouldn't be that critical for this operation because they're all exactly 380 thousandths. So what we're going to do now is we're going to just visually machine and mill close to those lines. I don't want to mill all the way exactly up to it. I want to mill and leave maybe a 32nd of an inch, maybe a 64th or a 16th, something away from that line so I can actually see the line still exists and I know that I'm in the inside of it. And I'm just going to do that manually and just visually. So that's kind of our goal here, is just to get this roughed out inside of there, close to the lines. And the lines are going to be pretty close too, but we're going to do some measurements to get those perfectly accurate. So we'll head over to the machine tool here. And today we're going to use the track mill here. This machine is very similar to the Bridgeports we've been demonstrating. The differences is it's a little newer. It has digital readout here that's a little more elaborate, and actually does have motor control for the Y-axis and for the X-axis. We won't be utilizing all that right now. We're just going to run it manually, but just to get you familiar with this machine a little bit. And we look at it, realistically, everything is pretty much the same as what we've learned so far. So, set my goods up here. And, I think I need that. Take our part, we're gonna put it in the vise. The vise is already indicated and trimmed in, so we're square. And we'll drop that down. What's kind of fun on here is this machine has a jog feature, so I can actually go to jog on this, and I can just hold this down and it'll move the axis for me.